In this example, we're told we're designing a Quonset hut for a military base. Quonset hut looks like this photograph on the right-hand side here. So it's basically like a half cylinder of radius r. And we're told that there's a wind speed of 30 meters per second coming in from the side, where the air pressure, is 101 kilopascals absolute, and air density is 1.2 kilograms per cubic meter. And we're told what the velocity field looks like over the surface of the hut, the top surface. So we're told that the radial component of the velocity over the surface here is 0, which makes sense because it's a solid surface. And that the tangential velocity over the surface here is minus 2 u infinity sine theta, where theta is measured from the right side horizontal of the hut. We're asked to find what the pressure distribution is over the top surface of the hut, what the net lift force is. The lift force is wanting to lift it upwards here. And we're also asked to find what the net drag force is on the hut. And then the very last thing is we're told that the air under the hut is at rest. So it's actually lifted off the ground. Unlike the photo here, we're just told it's lifted off the ground some small amount. All right, so to find the pressure distribution over the top of this hut, we'll make use of Bernoulli's equation. Since we're given the velocity field over the top, we can find the pressure using Bernoulli's equation. So what we'll do is we'll choose a streamline that goes from somewhere far upstream. So at this point, we'll call that point infinity, and then follows along the surface of the hut. Okay, so it's going along the entire surface there. So we'll choose this particular point right there since it's at an angle theta, and we'll find the conditions at that point. So let's write down Bernoulli's equation. And when we write this down, I'm going to neglect any elevation changes. Because we're dealing with air, the elevation changes won't really contribute much in Bernoulli's equation. So we're going to neglect that. And I'm going to apply Bernoulli's equation from that point far upstream to the point on the hut surface. So I'll just call it surface. And we know P infinity is P atmosphere. We know V infinity is just the U infinity. And the density everywhere is just going to be the same. So the density is going to be that 1.2 kilograms per cubic meter. So we're going to treat the flow as being incompressible. Now on the surface of the hut, we're trying to find the pressure. So the pressure on the surface is a question mark. The velocity on the surface squared will be that velocity that we're given. It'll be 4 u infinity squared sine squared theta. It's basically coming back up to this expression here. Radial component 0, but the tangential component is given by that. So I've just squared it here. All right, so we can substitute this in and solve for the pressure on the surface. Pressure on the surface will be the P infinity plus 1/2 rho u infinity squared minus the 4 u infinity squared sine squared theta. So I've just gone ahead and substituted in these terms into the equation and then just rearranged to find what the pressure distribution is. And we can write that a little more concisely by bringing the u infinity outside. So that's the pressure on the surface of the cylinder. We can write that in dimensionless form. What I mean by that is, if you look at this, we have dimensions of pressure here. If we do a little rearranging, let me go ahead and rearrange it. I'm going to bring the P infinity to the left-hand side and divide through by the 1/2 rho u infinity squared. If you look at that, this is actually dimensionless now. We've got pressure here, a pressure here. The denominator, this is a dynamic pressure, so it's like pressure over pressure, so that has no units. We call this a pressure coefficient. It's just a dimensionless pressure. And so the pressure coefficient for this particular case is 1 minus 4 sine squared theta. It's just another way to present the pressure distribution over the surface, but this time it's in a dimensionless form. And if you sketched out what that profile looked like, if you plotted it out, it'll look something like this. It'll be equal to 1 when theta is equal to 0, so if you plugged in a theta is equal to 0 here, this is all 0, and so Cp will be equal to 1. And then it drops below 0 and has a minimum value at pi over 2, where its value will be equal to minus 3. So it actually looks something like this, and then it goes back up to a value of 1 back at pi. So when theta is equal to pi over 2, this will be equal to 1, so it'll be 1 minus 4, and that gives us the minus 3. And then when we throw in a pi, this is also 0, and it goes back to 1. So when theta is 0, we're at this side. When theta is pi, we're at that side. When pi over 2, we're at there. So you can see that the highest pressures occur at the front point and the very back point, and the lowest pressure occurs at the top. Okay, so we actually have this kind of pressure distribution: high pressure here, low pressure here, high pressure again right back there. Okay. The pressure on the bottom surface, we're told here that air under the hut is at rest. So the pressure at the bottom of the surface is what we call the stagnation pressure. So the flow actually comes to rest. If I drew another streamline, one that came underneath the hut, it'll again start at infinity here, but here it's at a stagnation point. Actually, the stagnation point would probably be closer to there. But it's all stagnant conditions underneath that hut. So the pressure at the bottom of the hut, let me write that down over here. We can also find using Bernoulli's equation, so we can write this out again. Bernoulli's equation from far upstream and then under the hut. I should call this V instead of U. So I'll put a B here for the bottom. So we know the velocity at the bottom is 0 because it's stagnation conditions. So the pressure at the bottom is P infinity plus 1/2 rho U infinity squared. Or if you want to do it in terms of that pressure coefficient, so this is the pressure coefficient on the bottom, whereas the one up here was on the surface. So on the bottom here, this would just be equal to 1. So you can see on the bottom, if I draw the pressure on the bottom here, it's just going to stay constant like that. So you can see the pressure on the bottom will be higher than the pressure over the whole surface. So as a result of that, we would end up having an upward acting force on the hut. So let me erase some stuff here and kind of sketch it out for you. So the idea here is on the bottom we have an upward pointing pressure force I should say, right? And then over the surface we have a pressure that decreases over the top and then increases again toward the side. So here's the pressure distribution over the top. So you can see we have a higher pressure on the bottom than we do on the top, and so therefore you'll get a net lift force on the hut. So it'll want to lift off the ground, right? So that's actually the second part of the problem. So we've just done the first part, part A. What's the pressure distribution over the top surface? That's given right here, or in dimensionless form, it's given here. We also did the pressure on the bottom, that's given there. But now we're trying to find the lift force acting on the hut. And we're told, don't forget to include the effect of the air under the hut, which we described there. So let me work that out. So let's write out the lift force. And the way we're going to find this is we're going to integrate the pressure force. So let me redraw the hut here. So here's the angle theta at distance r. What we're going to do, since the pressure varies and the orientation varies over the surface of the hut, we're going to do it and find the pressure force over a little area, dA. The dA there is going to be r d theta times the distance in and out of the page. We'll call it b. And it has a normal vector pointed that way. So if I put that in terms of, let me put a coordinate system on here. So there's the y, here's the x direction. So actually, you know what? I'm going to do it in terms of radial coordinates. It'll just be, well, no, I'm sorry. I'll keep it in terms of x and y. So dA as a vector will be r d theta times b, and it'll be a cosine theta I hat plus sine theta j hat. So that's my little area vector. The pressure at that point we actually found up here, so we can substitute that in. And then we can get our vertical component of the pressure force by multiplying that pressure force times a sine theta. So the lift force will be the integral of the pressure, I'll just call it PS for the time being, times the area, r d theta times b cosine theta I hat plus sine theta j hat. So that gives us, oh, and then there's a minus because pressure acts inward, of course. I'll just sketch that in here. That's our little bit of pressure force pushing inward. So we have the pressure times the area, and there's a minus because it's acting inward. And then we just want the vertical component of that. So I'm going to just dot product this whole thing with the j hat component because I just want the vertical part. Okay, hopefully that makes sense to you. And then we're going to integrate that as theta goes from 0 to pi. So as we go from this edge all the way around to that edge. Okay, so that's due to the pressure force on the top, and then we also have this pressure force acting on the bottom down here. And that's all, of course, acting just straight upward and is uniform, so we don't have to do the integral there. So to figure out what that lift force is on the bottom, that's simply going to be a plus P on the bottom times 2R times B, the distance in and out of the page. So this is the pressure on the bottom, which we figured out right here. And then the 2RB is just the area. So here's 2R this way, and B is in and out of the distance in and out of the page. And that's already just in the positive y direction, so that's why we have the positive there. All right, so we could substitute in, one simplification we can make before we do the integral is we can do this in terms of a gauge pressure. So the P infinity would just be the atmospheric pressure. So we could do this in terms of gauge pressure where we don't have to include the P infinity there or there. It just will make things simpler if we do it that way. We can keep it in there if you'd like, but you don't have to. So then we would have, let me just write it all out. I'm just writing out the pressure first. So that's the PS right up there. When you do this dot product, you just get the sine theta component. And then we can solve that integral. Oh, in the PB, I should probably write what that is in terms of gauge pressure. It's just a 1/2 rho U infinity squared. So let's just simplify it a little bit further. There, I think I've done everything correctly here. What I've done is I've just pulled the 1/2 rho U infinity squared outside. I also pulled out an R and a B from both of those. And then I also multiplied through by the sine theta into here. And then at this point, we can go ahead and evaluate this integral. So that gets us into the calculus part. I'm not going to go ahead and go through the details of that, but it should be relatively straightforward to do that. When all is said and done, what we'll get in the end is the following. The lift should be 8/3 times 1/2 rho u infinity squared times 2r times b. So that's ultimately what you'll get. And the reason I wrote it that way is because we can define a dimensionless lift called a lift coefficient, which is just the lift divided by 1/2 rho infinity squared times 2r times b. It's kind of like the dynamic pressure times the area. The area is sort of the projected area you see from the top, and that comes out to be 8/3 if you make it dimensionless. Just another way to express the lift. You can express it both ways. So that would be the lift. It takes into account the pressure difference between the top and the bottom, and the way we found those pressures was via Bernoulli's equation. So again, the lift is caused by the pressure difference between the top and the bottom, and the way you find those pressures is through Bernoulli's equation. And then to find the force, you just take the vertical component of the pressure force. The last part of the problem is to find the net drag force acting on the hut. And there are two ways you could do this. The first way is you could do the same approach as what we have here, but just dot product this with the I hat, so you get the horizontal component. So this is still the pressure force on the top surface. And then when you dot product it with the I hat, you get the horizontal component. There would be no horizontal component to the pressure force on the bottom, right? It all acts just vertically. For the drag, we only want the x component. So this would be 0. This would be a dot I hat, and then you'd evaluate the integral. What you'd find is that that comes out to be 0. So the drag force comes out to actually be 0 in this case. We could have also found that a different way. The other way you could find it is just through the argument of symmetry. If you look at this hut and you just draw a center line here, you'll see that the left-hand side looks exactly the same as the right-hand side. So there's no reason there would be a drag force. The pressure exactly balances out. The pressure here exactly balances the pressure there. So you'd expect then, just from the argument of symmetry, that the drag force should be 0. So that way you can find it either way, but it's easier to use the symmetry argument. So let me just make a comment on how realistic this model is. It actually, this expression for the velocity field is actually a pretty good one over the front half of the cylinder. If you measured the velocity over this front half, it would be pretty close to this. It wouldn't be too far off of it. Where the model fails is the back half. In a real life situation, let me sketch the hut. What will happen is the flow will go over the top like that, and then you get what's known as boundary layer separation, where the streamlines would actually kind of continue on like that, and you get a recirculation zone here, where the flow would actually swirl back around. So the velocity field on the back half would not match this. It would be something different. So the pressure distribution back here would actually be quite different than what's on the front. And in fact, when you have this kind of recirculation zone, the pressure on the back half remains, to first approximation, nearly constant. So whatever the pressure was where it separated here, it would be the same pressure more or less on the back half here. And so you would model the pressure on the back half as a constant pressure right where that separation occurs. This also shows you that if you want to decrease the forces acting on this, especially the drag force. So if we have this asymmetric profile, of course, then in reality you would have some drag force because it's no longer symmetric from front to back. But if you wanted to reduce the drag on this, one goal would be to keep that separation point pushed as far back as possible so that you get a more symmetric profile. If I could push that separation point back to here, then the streamlines, let me draw them in a different color, would end up being more, actually I'm going to have to erase that because that didn't look very good at all. So if I could push back the point of separation to, let's say, here, then it looks more and more symmetric and you only have a small region of separated flow. And so since it's more and more symmetric, the drag force would be smaller and smaller because it would look more, the front half and the back half would look closer and closer to one another. That's a topic we'll come back to later in the course when we talk about boundary layer separation and drag forces. All right, so anyway, just to recap this example, the way to find the pressure distribution and the forces on this Quonset hut is we use Bernoulli's equation. Implicit in that assumption is that we're dealing with a steady flow. We're following flow along a streamline. We're assuming incompressible flow. And very importantly, we're assuming that the flow is nominally inviscid. So then we applied Bernoulli's equation and then found the forces by integrating the pressure force on a little bit of area and integrating it over the whole surface, also taking into account the pressure force on the bottom. Okay, we'll go ahead and end it there.